Hello everyone. We will present our work now on Equation Lab, which is a reinterpretation of the balance model for teaching linear equations in virtual reality.
Yes, a little about ourselves. My name is Morten Elkjær. I'm a PhD student here at DPU, Aarhus University.
And my name is Lui. I'm from Aalborg University, as well as EduLab. I'm an industrial PhD student. I have a background in human-computer interaction and research in virtual reality in general.
Yes, we are, as Louis said, industrial PhD students, which separate us for normal PhD students because we are affiliated at a company, and we met each other there and decided to embark on this journey together because we saw something exciting. My work as an industrial PhD student is mainly about the difficulties with linear equations of students from lower secondary school, and I work with equations in many ways, and this is one of them.
Yeah, and my project is on investigating the prospects and possibilities in using virtual reality in math education, or for types of knowledge that are more conceptual and abstract.
So, we would like to give you a little teaser about what we've been doing. We have designed this application, and this is a little teaser.
Right, so we just mentioned a bit about the motivation for the project and how it started, the interplay between our two projects. We will now start to introduce the problem that we're trying to solve and dive into the theoretical backgrounds behind some of the choices and requirements set for the design of the virtual experience and the teaching sequence that we have developed.
Yeah. Later on, we'll go into discussing the user study we performed using the teaching experience that Louis just told you about. So, as an introduction, last year, Otten et al. Came out with a literature review on how the balance model has been used for teaching linear equations through history, and they find that though the model has several affordances, it also comes with some limitations for teaching linear equations. And the most obvious limitation is actually presented by Vlasis in 2002, is that when it comes to negative numbers, the balance model is not sufficient anymore. So the aim of this study is to investigate the prospects of using virtual environments to account for the limitations of the balance model as a tool for teaching linear equations in virtual reality. So this is what we're going to show you now. We have, of course, chosen to design this application. So the application itself is not the design of the application is not actually a part of the research question, but this is the research question that we worked out from. So with emphasis on manipulating negative numbers and with emphasis on equation solving strategies, how can this immersive experience using a reinterpretation of the balance model support students' understanding of the concept of linear equations? That was a long sentence. We know this, but hopefully you'll understand, right? So, and based on a user study, how can we, what influential factors can be identified and how can we overcome or enhance the effects related to the transferability from the virtual experience to pen and paper? Because we know, of course, that students will not be walking around in virtual reality all day, all year, solving equations. This needs to be done on pen and paper in the classroom. So we're quite aware of that this is not a solution.
Isolated, experience. Yeah.
So we will present to you some theory that paved the way for this design and for the teaching sequence. But we'll actually talk about what does it mean to understand the concept of linear equations. And we at the outset we have is these two types of difficulties presented by Uffe and Mogens in 2015. I believe they got them from Caroline Kieran. The first kind of difficulty is to do with the goal-oriented transformation of the equation. So what manipulations are possible, are allowed, and how do we end up with an equation that is equal to the one we just had after doing transformation. So this is the first kind of difficulty. The second kind of difficulty is to do with what is an equation and what is a solution. So this is more of a fundamental level. Traditionally, the balance model have several looks. This is just a few of them. Vlasis presents this one in her teaching experiment, where you have the unknowns present as a singular object. So you have one of the unknown, and there will be 7 of them on the left side, and then some number and 3 on the other side. This, of course, affords that you can remove equal parts from both sides of the balance model to end up with an equation equal to the one you just had. On the second option there, you actually have a different representation. You don't have numbers present. You don't have unknowns present in the same way. You have objects, right? But in this way, you can use the balance model interpretation of equality to determine what is exactly would a triangle be worth in some way, right? And the last one is one me and Jeremy and Dietmar used for some diagnostic tasks, but that is just to demonstrate another look that you could actually have the algebraic notation present on the balance model. In this case, it represented centicubes or coins of similar size. So this is just to show you that, but more on the affordances of the balance model for teaching linear equations. In this literature study we mentioned before, they find that there are 3 rationales for using the balance model for teaching linear equations. And these 3 rationales mentioned in the literature is that on the balance model it's very clear and it's very convenient to understand the concept of equality when using the balance. None of the arithmetic thoughts that could be related to the concept of equality. For instance, you have some students thinking that the equal sign means that now we have to calculate something and the result will be on the right side of the equal sign, and it's just an operation to the left. That we don't have on the balance model. The second rationale has to do with physical experience, that you have an opportunity to, when you have a real dynamic balance, you have some sense of what does it mean to maintain balance. What do I have to do to each pan to maintain balance, and how can I work with this scenario? The third rationale has to do with learning through models and different representations. So when you're presented with the balance model, you get algebraic notation in a different representation, and that can lead to better understanding. The clear limitations of the balance model is also mentioned, and as we mentioned earlier, negative numbers are difficult to apply when using the balance model. It's difficult to work with negative numbers, negative coefficients, negativity in general. And there's actually one more, that on the balance model we don't have operators present. Everything on each pan is added, and this is how we see, and this is how the balance model work. But if things are subtracted in an equation, we have this detachment of the minus sign, as Herkovits and Linchevsky mentioned, that the operator minus is not necessarily seen as influencing the number following it. Fioi and Rojano in 1989 made a categorization based on linear equations based on based on working on the unknown, operating on the unknown. And then they have these arithmetic equations that would be something where you only have the unknown in one member on the left side or on the right side, and on the other side you would have some numbers, right? And a non-arithmetic equation would be equations with unknowns present on both sides. Vlasis expands this categorization into finding that we need another layer of abstraction in some way, that the negativity causes major problems for students when working with these equations. So you could have this equation minus x equals 7 is extremely difficult to students to understand what is going on, even though it would simply be an arithmetic equation in Fiore and Rosciano's categorization. Similarly, the equation minus x equals 24 follows the same pattern, and same with the non-arithmetic equations. You find that negativity in general leads to more abstraction, and that's. We actually chose these two equations, and we pursue to use these equations in our teaching experience because we find them very nice and very saying about these very useful when using negative numbers. Yeah, should I say it that way? Yep.
Yeah. So we may say that the balance model creates an analogy between numbers and mass of objects. But when we think about negative numbers, then we have probably a hard time imagining objects with a negative mass, which is where virtual reality or virtual environments may come into the picture. Yeah, so I'll just go to the next. Yeah. So I will just briefly explain a bit about the relation between virtual environments and virtual reality. A virtual environment is something that's seen to be mediated. It's a mediated environment, and it may or may not simulate reality, depending on the purpose or objective of the experience. So this simulation is the part of the experience that is programmed, and the programmed behavior is what we can control to simulate whatever is needed for our purpose. And so this mediated environment can then be perceived through virtual reality, so to say. It is perceived through a combination of different components. A common VR system entails 3 different types of components, usually a head-mounted display that you're wearing, providing stereoscopic vision as we perceive the real world. Motion tracking to map the motions of the user from the real world to the virtual world. And then input devices that makes it possible to interact and move and engage with the environment so that it becomes dynamic and feels alive. Yeah. As I just mentioned, the combination of these type of sensors and displays and so on provides the user the option of being able to move and to interact in 6 degrees of freedom. As we can see here, a picture from a mixed reality capture, meaning that we see Morten superimposed into the virtual environment, grasping or reaching for an object. He is capable of moving in all directions. Yeah?
Yes.
And so this was a bit about the technological possibilities and how a common VR system is constructed. In VR, we also talk about the sensation, the psychological sensation that you experience when you are in VR. And this is often related to the concept of feeling present. In this case, there are 2 distinctions between what you might experience. There is a place illusion where you actually feel like you are present in a different place from the location that you're at in reality. And the plausibility illusion is that you actually accept the premise and the scenario that you are present in, feeling present in. So we believe that this programmability and the immersive powers of VR can be used to perhaps overcome some of the physical or some of the general limitations of the balance model.
Yes. Now we step into the design requirements we set up, and Louis will present those to you in a few seconds, yeah?
Yeah. So we have 3 of these requirements. The 2 last one limited slightly, but the first one is simply that we want to visualize and present the balance model as being recognizable. It needs to be still maintaining the characteristics of a balance as we know it from the traditional examples, however with a modified real-time physics simulation so that the program behavior of the balance can accommodate negative numbers. And so the second requirement is that the term of an equation, whether it being constants, coefficients, or variables, should be represented visually in a uniform way, except for the algebraic notation. So you see sort of a virtual object being the same in shape, color, and so on, but what is different between each term is the algebraic notation itself, as being the only difference. Finally, we want to allow students to experiment and to solve equations in this environment. Therefore, we need a system that allows you to transform the terms of the equation. And yeah, after this, we can now go into the design of how we actually implemented these requirements. And yeah.
Yes. Yeah. It says some limitations here. We limit it to integers and integer coefficients simply because we're dealing with lower secondary school students. There are no need for fractions or decimal numbers. There is no need for brackets and stuff like that when you're dealing with just negative numbers in focus. So we chose that, and the transformational part of it, we limit that to exclude multiplication, and we did that for a reason, and we'll tell you about that in just a second.
Right. So here you have first an overview of the virtual environment with the balance model presented here, a so-called workspace where you're able to do transformations. And in this area over here, we will have objects spawning after you perform certain transformations.
When Louis says spawning, he means appearing.
Yeah. Sorry. So if you go to the next slide. Here we see just the requirement.
Sorry. There you go.
Yeah. Just simply, as we stated, visually recognizable. This has sort of the same structure as a traditional balance, two pans, a beam connecting them, and what we added was a little bit of color coding to the beam, so that in the case of not being a balance, you see a yellow color, and in the case of being balanced, it is turning green.
Yes.
So here we have a term represented. These are the same for any type of term, whether it being a constant, variable, or coefficient. And these are interactive, so this is what the user actually interacts with and moves from the balance model to the workspace area, which we will talk about now. So the workspace area, allowing for transformations, registers and provides options depending on the number of present objects. So if you have a single object presence, you are given the three options of splitting, inverting, and dividing by. Yes. In the case of,
Should I? Yeah, I would just like to explain these mechanics to you, and because they're really important, and you might agree or you might disagree, and it's very interesting to us how you will perceive this. So we wanted to be able to give the user the possibility to use the affordance of moving equal parts from both sides, right? So in the case that we have the equation, let's say 7x plus 5 equals 33, you would like maybe to remove 5 from each side of the ball. That's why you got the option of splitting. You put the object 33 on the workspace, and the slider will let you move left or right, and the two numbers on the slider will sum up to 33. So you can split into a 5 and a 28, and then pull the string downward, and the object will explode, and you will get a 5 and a 28. And then you can put them back on the balance and remove 5 from each side. That's the purpose of that one. So you have that. The invert mechanic is very dear to us. Because inverting things additively is not necessarily part of secondary or lower secondary school, but the mechanic felt like the good choice for us, because we didn't want to give the students opportunity to multiply by -1. We didn't want to, or should we give them the opportunity to divide by -1? So so that's instead we went with the invert mechanics. So you can invert every object. So let's say you have -6. You invert it, you get a 6. So and then you can work in that way. And that's mainly implemented due to the equation you saw just a minute ago, -x equals 7. The only way you're able to solve that is dividing by -1 on each side, multiplying by -1, or in our case, inverting each side, right? The last thing we chose that the students should be able to solve equations like 3x equals 9, and then you probably want to divide by 3 on each side of the equation. So you get the opportunity to divide by a non-trivial positive factor or divisor, what do you call it, in the number present, or the coefficient of the term present, right? So in the case you put -6x on there, you will have the option to divide by 2, 3, or 6. So positive integers or non-trivial divisors, right? And the number itself.
So this was the case of a single object being present. You are provided these options. In the case of multiple objects, you get the option of adding together. And this was primarily done to allow the students to go into a sort of experimentation mode where they are able to take decisions. They might make an error, but the persistence of the objects, meaning that if you divide the object of 5x by 5, you are actually left out with the entire thing, but then you can pick the 1x to put on the scale or the balance. But this also works with you being able to take a decision, make a transformation, but then also cleaning up and sort of adding them all together so you can redo whatever you need to. Yeah? Mm? So, here we have a video clip.
Yes, this is the equation you saw before, right, from Blas's. -6x equals 24. And now our virtual guy will solve it for you using the environment, so you can have a look at what we just tried to explain to you. You see the beam is green, the balance, the way the balance is balanced, yeah, and and now the user can pick up the -6x. And you get the options. You see you can split it into -3, -3, and then you get -3x and -3x. So they add up to or you could invert it. So now the user has inverted it into 6x. And if you put that back, it actually pulls up, and you can have a think about why. And so the object explodes, and you are left with the inverse. So now you can put that on the balance, and you see you restored balance, right? This is very common used sign language. So now the user might want to divide this to extract a single unknown. And so he pulls the slider, so divide by 6, and then realizes that must be the same number. Yeah. The object explodes, and you're left with 6 x's. We chose to give the user these Windows hands because you only needed one point to interact with, right? You don't need a hand to grab stuff, and that was the easiest part to understand. And so you get the sound, and the equation is solved, right? You have a single x, and you have a -4 on the other side, and you can see that now you solve the equation. Yes. We realized that our design choices has made the strategy of change sign, change side, change signs as a possible option. And we know that this strategy might not be a favorable strategy to teach to students right away, because it might not give them a better understanding on what does it mean to solve a linear equation. You would rather that they subtract 5 from each side instead of just moving the 5 to the other side and put in a minus in front of it. But we believe that in our case, you actually, because you have the exploratory environment, you get an added benefit to the change side strategy. You could actually talk to the students about what does it mean to push down on one side. Is it the same as pulling up on the other side? So instead of having 5 pushed down on one side, you could arguably tell the student that wouldn't it be the same to have it a -5 and then pull up on the other side? So then you can talk about that, and then you can talk about what algebraic expression you actually have afterwards, and why this strategy actually could. We believe that this could be beneficial, and this could be a fun way to teach students about linear equations. And this is only provided because the balance is real time and dynamic, right? It showcases what is actually on it. So even with negative numbers. So,
yep.
Now the user will solve the equation you also saw, the one from Baudin, 1993, where you have this is a special case of equation, right? Because this have negative numbers. If you want to collect like terms, you might want to collect the unknowns on the right side of the equal sign, because there's 13x over there and you have 7 on the other side, and is that a good strategy to have the x's on the right side and stuff? You can go into all of these discussions with the students, and hopefully the balance model as a tool eliminates some of this, because things are just intuitively equal when in another way than just. But here you see that we can invert stuff and retain balance by moving it to the other side, and we realize that it might be difficult to understand when the solution is negative, but nonetheless. So now we showcase the add function, where you add 7 and minus 13x together, and you get minus 6x. I hope you like the music. It's very quiet. He's being very nice to you, the user. He's showcasing a lot of functions. So now we're left with something like before, right? And then you can divide this by 6 and divide the other side by 6, and then you. As a side note, the blue crystals are what fuels this world with energy. And of course he divides that side by 6 also. And he gets a minus 3. Bling. Very nice. So what did we do with this? Now we have an application, and we wanted to do a user study, right? So we got in touch with a school in Denmark, and they agreed to give us 10 students to try this application with. And our motivation going into this user study was just to gather as much relevant data, or at least seemingly relevant data as possible, right? So we wanted to get everything from everything out of these students that could maybe inform something about this teaching experience, right? So what we did was
we used a number of different techniques. Some of them were more to observe behavioral cues afterwards in the data analysis process. So we used a technique, for example, called mixed reality capture, which was, maybe you recall from earlier, the picture of Morten being superimposed on top of the virtual environment. This technique we have used for all the students, so we have video recordings of them behaving and acting inside of the environment. We thought that might be an interesting way to extract certain cues about maybe understanding or the behavior inside. This is a very unexplored area, the methodology of assessing conceptual understanding or whatever effect this type of experience has. So we just tried to collect as much relevant data to try and conclude.
And we got to go back to the school to talk to the teacher. They agreed to do this 2-week trajectory with equations after we left. And then we came back after 2 weeks and talked to the teacher about what he saw in class. So let's go. As I said, it was a sample size of 10. We got 6 boys and 4 girls from the 7th grade. And they were chosen by the teacher to participate based on, what do we call it, performance level in some way. So we had low performance, we had medium performance, we had high performance. And we tried not to know this before the teaching experiment, but they had done a pretest, but we waited to analyze the pretest until after the teaching experience. We want as raw an image of the students as possible when doing the teaching experience. It took approximately 1 hour per student. We introduced them to the display and the controllers and the environment, and then we gave them a guided teaching sequence using equations you will see in a minute, and then we did exactly the same using pen and paper, and everything is videotaped, and lastly they did a self-reported questionnaire. Yes, yep. So this was the teaching sequence. So on the left you have what we did in Equation Lab, and on the right you have what we did on pen and paper. And we gave them, you see the difference between the two is the 2 top ones on Equation Lab. We gave them the opportunity to play around with some elements, some objects before we actually started them, asking them to solve equation with us. So they got familiar with negativity on the elements. We asked them to invert the -4 to get a 4 to see how the balance reacted to this, and then we went into giving them these equations. They actually solved these equations just by looking at them. They didn't have the need for the balance to solve the middle two. They know that the solution to the top one is 3 and the next one is 4, right? But then we went on using the balance model with them to give them an idea on how they could be solved using this tool. And then we went on solving these two we chose with negative numbers, and we asked them all, what do you think about this equation? It looks weird. There's a minus sign there. It looks weird. So they didn't like this one at first, but using the tool, they found it very, very fun. So, and then we did the same thing on pen and paper, and just to observe, was there any transferability just immediately doing the same equation? Could they do it again in the same fashion? And they reported that they found it easier doing it in the virtual reality, even though you just have to write in a 5 by 5 centimeters on a piece of paper instead of going like this all the time. But one funny story from doing it on pen and paper, we actually had one girl who wanted to draw the workspace on a piece of paper to move the terms from the equation on pen and paper over there, divide it by something and move it back. It was quite nice to see. She really liked the application, but yeah, let's go on.
Right. So we were also interested in just taking a little test of how the students' affective response to this was. or the attitude towards this whole teaching sequence. So we used a quite commonly used game experience questionnaire to assess different components related to competence or to the positive effect of the experience. This is all self-reported. There's a clear subjective bias in this, but we were interested in how they affected response regardless, which is also connected to the fun that Morten is mentioning. So we would have questions such as, I felt skillful, I felt challenged, I felt bored, I felt content. And the students were just to simply rate it on this 5-point Likert scale. And we will go into the details of the result later on.
Yes, we will just give you a brief overview of the pretest. I know this is a lot of text, but we'll just go over it really quickly because the interesting part is at the bottom. So we gave a pretest of 14 items, and some of them are quite classic items, and some of them I made up. But the first one, you might know the top one. The obvious answer is 12, right? So actually 50% of those 10 students answered 12 in the first one. And that just showcases the procedure of reading something like this. These equations, all these 4 were actually solved using guess and check methods. No one used a proper formal transformation to use this to solve that one. Maybe that's why only 50% of the students got it right. And even though these equations might seem easier, just looking at them, they were actually quite a lot harder, right? Only 20% could answer this one, and only 30% could answer this one. So it really proves the point that having negative solution is difficult, right? Yes. Okay. So now I need to remember everything. But we had one interesting case. When we went back to the school, we had an interview with the teacher of the class, and he reported that it has been fun doing 2 weeks of equations in class, and it's one child especially had some interesting behavior. This guy Albert, he used the invert mechanic in class. So he told the teacher, now I just invert this item and put it on the other side, and with direct reference to the balance model. So he could perform the change side strategy to some extent, and he could solve equations like minus ax equals some number, right? He could solve these equations. However, we got to get another interview with this guy, Albert. So we brought him in, and next slide, please. So and then we solved additional 5 equations with him. So if we start from the bottom, he was actually able to solve this one quite easily because he was able to just invert each side, and then he told us he does not understand this. This makes no sense to him. If he just guessed, he would guess the answer would be 6. But yeah, I mean, 5 times 6 is 30 there, and then minus 5, then you get 25, something like that. So it makes sense that his guess would be 6, right? But using the invert mechanic, he was able to solve it quite easily. But is it proper understanding? Well, no one knows, right? So, but we would, if we go to the next slide, the equation number 4, this one on top. He rewrote this into the second line, and he explains to us that because he subtracted 10 on the right side in equation number 2, you should add 10, right? He explains that the gap between the minus sign and 10 was too big, so he did not consider it to be a part of to be influenced the 10. So he used the invert mechanic, but he was not able to distinguish what influenced what, and so we realized there's a gap in the teaching there, right? So if we are to teach this strategy using this tool, we should accommodate for this problem, right? So let's move on, Louis. Yeah.
Right, so I'll just quickly describe some of the more prominent results from this. Generally a very positive response, effective response from the students. As you see here, not at all level of tension or annoyance. These components are based on different questions, and we had 2 items for each of the component. I'm just going to highlight, that there was no tension or annoyance by the experience, and they felt fairly or extreme levels of positivity, sort of that they felt content and they felt good. In regards to competence, they also said that they felt skillful and that they felt successful, which is, I think, a quite nice result from a child at this age working with linear equations. But yeah, that's about it for this very subjective little questionnaire-based affective response.
This is very important to us,
evaluation.
that they actually found it fun and engaging. It says something about the teaching technique in some way, I believe. Okay, right. So if we return to the research questions, so what can we actually make from this? Not much, but we believe that this new way of teaching the change sign, change side strategy can be beneficial to students. The invert mechanic alongside this with the dynamic approach to the balance model where you're able to work with negative numbers, we believe that this could have some positive influence on how students perceive transformation of equations. If we go back to the 2 types of difficulties Uffe and Mogens writes about in 2015, it's actually the transformation, and it's the equation itself, right, and the solution. So regarding the first one, we believe that this change side strategy can be viable in this environment, and it could be taught in a meaningful way, because pushing and pulling up on the pants. And if we go to the second approach, or the second kind of difficulties regarding what can be a solution to equation and what is an equation, we believe that an environment like this actually affords the solution of negative, understanding negative numbers as solution to equations, because the physics are there, right? They're in there in some way, and you it's not magic anymore. It works. Right.
And so, based on this short user study, we should also try and identify what kind of factors that led to the level of transferability that was identified, perhaps in the case of Albert. We have a few ideas how to overcome or enhance these effects, but of course this requires a lot more rigorous research. But we're definitely, as a starting point, very interested in investigating the transferability of different design principles and requirements related to transferring from the virtual environment to a pen and paper exercise in a more real setting. And so this could, for example, be by presenting more representations. So here we have a new iteration of it, providing the student with a little blackboard visualizing the algebraic notations or the content of the balance bands. And here we write it up dynamically according to what is present, so you get 2 types of representations.
Yeah. Yeah, and when the balance is not balanced, it will change to a not equal sign in the middle. And we would like to implement the option of having the teacher being able to choose if there should be a smaller than or greater than signs present there, but that should be an option for the teacher to have in our, because we realize, and some questions might come of this in a moment, we realize we're helping the students here, right? We realize that we're doing calculations for them. We realize that if you're not able to know what minus 13x plus 7x is, the system will tell you, right? So we realize this. There is some limitations too, but in our it's not the intention that we should teach the students how to calculate. We want to teach them about linear equations, right? And maybe it's intertwined and maybe it's not. So, yeah. With that, thank you.